So in the previous question, we looked at the titration of a strong acid and a strong base. In this case, we have 50 milliliters of 0.1 molar ammonia is titrated with 0.15 molar HCl. The Ka of ammonia is this, the pKa is that, and it just says these questions are challenging, which is an understatement. So basically, we have 50 milliliters of a weak base being titrated with a strong acid. And just like in the previous question, we're going to look at different points along the titration in order to determine the pH. But as you'll see, it is considerably more complicated when we have a weak base or a weak acid being titrated with a strong base or acid. So that's basically how it works. So first things first, it says, what is the initial pH of the solution? Well, this is just like the previous chapter. What we have is a weak base in solution. We have 50 milliliters of 0.1 molar ammonia. So when we want to find this, we want to do it just like we did in the previous chapter. But before we can do that, we're given the Ka and we need the Kb. So if you remember, the Ka times the Kb equals Kw, which is 1 times 10 to the minus 14. Or the Kb equals the Kw divided by the Ka, which is 1 times 10 to the minus 14 divided by the Ka, which is provided 5.68 times 10 to the minus 10. And when you do that math, you find that it's 1.76 times 10 to the minus 5. Remember that the Kb is equal to, if we have ammonia reacting with water, because at this point we only have ammonia in solution, the concentration of NH4 plus times the concentration of OH minus, because it reacts with water, over the concentration of NH3. Now, if we do the ice table, the initial concentration of NH3 is provided to us as 0.100. The initial concentration of NH4 plus is 0. The initial concentration of OH minus is 0. But this will react with the water. So the change is we're going to lose some X amount of NH3, and we're going to gain some X amount of NH4 plus and OH minus. We're going to assume that this X is negligible, although you could test to see if it's less than 5%. We're going to assume it's less than 5% here, or 5 to 10%. And here we have 0.1 molar. Here we have X, and here we have X. Now, let's plug in what we know. Well, we know Kb is 1.76 times 10 to the minus 5. We know NH4 plus is X, OH minus is X, and NH3 is 0.100, where we again ignore the X. We could check, but we're going to assume this is less than 5 to 10% as it is in the examples that I've given. So now we do the math. X squared equals this times 0.1, which is just going to be 1.76 times 10 to the minus 6. We take the square root, only take the positive answer, and we find that X is 1.33 times 10 to the minus 3 molar. Okay, so it's about 1% of this, a little over 1% of this. Actually, it's 1.33% of it, but certainly less than 5 to 10%. Now, we have to realize that the concentration of X, or X, is the concentration of OH minus. Well, now we can find the pH. Specifically, we can find the pOH, which is equal to the negative log of the concentration of OH minus. So the pOH is going to equal the negative log of this 1.33 times 10 to the minus 3, and the negative log of that is 2.89. So the pOH is 2.89. As you'll recall, the pH is 14 minus the pOH, so if we take 14 minus 2.89, we find that the pH is 11.11 as the pH of this solution. So in this example, at the beginning of the titration, we only have a weak base solution. So this question is identical to one of the questions at the end of the last chapter, where you just had a weak base in solution, because before the titration begins, you just have a weak base in solution. Now, let's look at what happens when we start to add some of this 0.150 molar HCl. All right, so this question says we still have the 50 milliliters of the 0.1 molar ammonia, but now we've added 15 milliliters of HCl. So we're titrating the 50 milliliters of 0.1 molar ammonia, and now we're adding 0.15 molar HCl, and we've added 15 milliliters. So in the previous example, I did it by moles, and here I'm going to do it by molarity. Specifically, I need to find the concentration of NH3 initially. And to do that, I need to use C1V1 equals C2V2. Why? Because there's been a volume change. Specifically, I had 50 milliliters of solution, now I have 65. So my 0.15 molar has been diluted by the change in concentration. So the original, the 0.1 molar has been diluted by the change in concentration. So I had originally 0.100 molar, and I had 50 milliliters of it. The final concentration is what I don't know, and the final volume here is going to be 65 milliliters, and 65 is 50 plus 15. So initially, I have 0.0769 molar NH3. What about H plus? Well, for the concentration of HCl, or the concentration of H plus, they're the same because it's a strong acid. I'm going to again use C1V1 equals C2V2. In this case, the initial concentration is 0.150 molar. I have 15 milliliters of it. The final concentration is what I'm trying to figure out, and the final volume is still 65 milliliters because I added the two together. And in this case, I find that the concentration of H plus before the reaction starts is 0.0346 molar. Okay, so what you'll notice is the concentration of NH3 is higher than the concentration of HCl. Said another way, I have not reached the equivalence point. So now I need to figure out these concentrations down here using the ice table. So what I have is 0.0346 molar H plus. I have 0.0769 molar NH3, and I have 0 molar NH4 plus. So what's going to happen here is this H plus is going to react with the NH3 to form NH4 plus. But at the beginning, I don't have any NH4 plus. I only have NH3. Well, because the H plus is left, I'm going to lose all of it, 0.0346 molar of this, and I will not have any more H plus left because it's all going to react with the NH3. I'm going to lose 0.0346 molar NH3, but I'm going to gain 0.0346 molar NH4 plus. Why? Because as this H plus reacts with NH3, it converts this into this. Specifically, 0.0346 molar of this is going to be converted into this. When I subtract these two numbers, I find that this is 0.0423 molar, and this is just going to be 0.0346 molar. So now what do I have? Now I have a buffer. My buffer contains both NH3 and NH4 plus. Well, how do we determine the pHs of buffers? The pH equals the pKa plus log of the concentration of base divided by the concentration of acid, as you've seen before. So in this case, the pH equals the pKa, which is provided in the previous part of the problem, which is 9.25, plus the log of the concentration of the base, which is this one, the NH4 plus, the NH3 is the base, sorry, it's a weak base. The NH3 is the base, so 0.0423, divided by the concentration of the acid, which is 0.0346. So we have more base than acid, so our pH should be slightly higher than our pKa, and when we do that, we get 9.34. Indeed, it is slightly higher than the pKa. So what is the take-home message of this? There's a couple things to remember here. First of all, we have a volume change. When we add this to this, the total volume is 65, so we need to do C1V1 equals C2V2 to find the concentrations before the reaction starts, if you will. Also, we need to realize that NH3 will react with H plus to form NH4 plus. NH3 and NH4 plus both being in solution is a buffer. So we're going to use the Henderson-Hasselbalch equation to find the pH of the buffer. What makes these questions particularly challenging is knowing which equation to use and when. The best thing you can do, practice. So it says calculate the pH at the equivalence point. And I'll just remind us that we have 50 milliliters of 0.1 molar NH3 being titrated with 0.150 molar HCl. We also know the Ka and the pKa of the NH3. This information was all provided in the original question. Note we're on part C now. All right, so it says calculate the pH at the equivalence point. Well, in order to do this, we need to know how much NH3 needs to be added, or excuse me, how much HCl needs to be added in order to reach the equivalence point. So we have H plus reacting with NH3 to form NH4 plus. Now, when we do this, okay, reaction, at the equivalence point, all we're going to have in solution is NH4 plus, which means the NH4 plus is going to interact with H2O to form H3O plus and NH3. Said another way, because we have all of the conjugate acid in solution, the pH should be slightly lower than 7 at the equivalence point. That being said, it's quite a bit of work to figure this out. The problem is we need to know the volume of HCl that we're going to use in order to reach the equivalence point, because with that we can then find the concentration of NH3 that is going to be there, but the NH3 isn't going to be NH3 anymore. It's all going to be NH4 plus. So we need to do quite a bit of math. So first things first, let's find the volume of HCl required to reach the equivalence point. To do that, we need to convert from liters of NH3 to moles of NH3 to moles of HCl, and then we need to convert that to liters of the HCl solution. So we're trying to find the total volume. We're basically doing stoichiometry here. We are doing stoichiometry here, all right, in order to find the total volume of HCl that's required. Well, we know that we titrated 0.0500 liters of NH3 solution, and we know that we need to convert it to moles. Well, we know that it's 0.1 molar. So for every 1 liter of this NH3 solution, there's 0.100 moles of NH3. We know that the reaction is 1:1. For every 1 HCl, it reacts with 1 NH3. So for 1 mole of H plus or HCl, remember they're the same because it's a strong acid, it's 1 mole of NH3. We also know that the HCl is 0.150 molar. So in order to do that, we need to do 1 liter of the HCl on the top and the 0.150 moles of HCl on the bottom. And when we do all that math, we find that this is 0.0333 liters or 33.3 milliliters to reach the equivalence point. Now we need to find the concentration of NH4 plus. Well, it turns out that all of these moles are equal. The moles of NH3 and the moles of NH4 plus are equal. So if we convert liters of NH3 to moles of NH3, we can then convert it to moles of NH4 plus because they're 1:1. This forms one of this, and then we can divide that by the total liters, and that'll give us the molarity of NH4 plus. So in this case, we're going to start with the same liters of NH3, which is the 50 milliliters, 0.0500 liters of NH3 times 0.100 moles of NH3 per 1 liter times, now we got to convert to moles of NH4 plus, but they're 1:1, so 1 mole of NH4 plus per 1 mole of NH3 times, now we need to divide by liters. We put a unitless 1 on top, that moves the moles over, and then we divide by the total number of liters. The total number of liters is the 50 milliliters plus the 33 milliliters, which is 83.3 milliliters, which is 0.0833 liters. And when we do that math, we find that it's 0.0600 molar NH4 plus. So all that math now allows us to do the same thing that we did in the previous chapter. We now know the initial concentration of NH4 plus here, and this NH4 plus is going to interact with water. Note that the H plus is gone. Okay, the H plus from the acid is gone because it's all formed with the NH3 to form NH4 plus. So the only pH change here is going to be from the NH4 plus interacting with the water itself to form H3O plus and NH3. So specifically, we're going to use the NH4 plus, which is going to be 0.0600 molar. The initial concentration of H2O plus is 0, and the initial concentration of NH3 is 0. Remember, we're now ignoring this previous reaction because we've turned it all into this. So all we have is this in solution and this interacting with water. This has all been neutralized. All right, the change, we're going to lose x of this, and we're going to gain x of each of these. And what we end up with is 0.0600. We're going to go ahead and ignore this x. We're going to assume that this is less than 5%, although we could check it. And we get x, and we get x. Now we can plug in. The Ka for this reaction is going to be the concentration of H3O plus, products over reactants, times the concentration of NH3, divided by the concentration of NH4 plus. All right, so the Ka, which you remember were provided, which is 5.68 times 10 to the minus 10, equals x times x divided by 0.0600. Cross multiply, okay, or multiply both sides by 0.06, either way you want to look at it, and you get x squared equals 3.48 times 10 to the minus 11. Take the square root, and you find that x is equal to 5.48 times 10 to the minus 6. But what is this? This is the concentration of H3O plus. Okay, so this is your concentration of H3O plus. Sorry, it's off the screen a little bit there. So we know that the pH equals the negative log of the concentration of H3O plus. So the pH equals the negative log of 5.48 times 10 to the minus 6. The pH equals 5.234, which is slightly less than 7 because we have a weak conjugate base in solution. This is complicated, all right, and it takes a large amount of practice to master how to do these problems, because not only are you having to do all this math, you have to realize which math you need to do. Good news for part D, there's an easy part here. What is the pH at 1/2 the equivalence point? Well, at 1/2 the equivalence point, if we look at the Henderson-Hasselbalch equation, which is pH equals pKa plus log concentration base divided by concentration acid, at 1/2 the equivalence point, the concentration of the base and the concentration of the acid are equal. This is 1. The log of 1 is 0. So the pH equals the pKa. The pKa here is 9.25, so it's just 9.25. So thankfully, something here is easy. So at 1/2 the equivalence point, the pH equals the pKa. All right, so this last one says a 50 milliliters of 0.1 molar ammonia solution is titrated with 0.15 molar HCl. What is the pH after 38 milliliters of HCl is added? So if you recall previously, we were before the equivalence point. And what you're going to find here is we're actually after the equivalence point. So the first thing we need to do is we need to find the concentrations of ammonia and HCl in the diluted solution and figure out which one we have more of. So this is very similar to what we did before. So the concentration of NH3 is going to be found by C1V1 equals C2V2. Okay, you can't use the values from before because before we added 15 milliliters and now we added 38, so the total volume is going to be 88 milliliters. So we have a different total volume. But in this case, the initial volume is 0.100 molar. The initial concentration, sorry. The initial volume is the 50 milliliters. And the final concentration is what we want, and the final volume is 50 plus 38, which is 88 milliliters. When we do this, we find that C2 is equal to 0.0568 molar. And we want to repeat for HCl. All right, and when we do that, we're going to want to do C1 V1 equals C2 V2. C1 for HCl is different, 0.150 molar. The V1 is the 38 milliliters this time. The C2 is what we're looking for again, and the V2 is still 88 milliliters because we mix the two together. When we do that, we find that the concentration of the HCl is actually higher at 0.0648 molar. So in this case, we actually have more HCl than we do NH3. So if we look here, we have H plus NH3 yields NH4 plus. Well, the acid concentration here is 0.0648 before the reaction, and the concentration of NH3 is going to be 0.0568 molar, and NH4 plus before the titration is 0. When we add the acid, in this case, we're not going to use all the acid up. We're actually going to use up all of the NH3. So we're going to use up 0.0568 molar NH3 because that's all the NH3 we had. Said another way, we have more acid. In the previous case, we subtracted out all of the acid, but this time we have excess acid. For the concentration of NH3, we're going to lose all of it, 0.0568 molar. And for this one, we're going to gain 0.0568 molar because all of the NH3 is going to be converted to NH4 plus. When we do this, we're going to find that it's 0.00800 molar H plus. We're going to have no NH3, and we're going to have 0.0568 molar NH4 plus. Now, you're going to have a small amount of this weak conjugate acid, NH4 plus, but you're going to have strong acid. The strong acid is going to overwhelm this. So the pH is only going to be dependent on this excess strong acid. We're going to basically ignore this concentration because it won't have a significant difference on the pH because this is a weak acid and this is a strong acid. So the pH here is simply going to be the negative log of the concentration of H3O plus. Again, we ignore this because it's a weak conjugate acid and this is a strong acid. So in this case, it's going to be the negative log of the 0.00800 molar, and the pH is going to be 2.097. Okay, so this is how we find the pH. These questions are incredibly complicated and take practice.